Hi everyone. Today let's talk about session 14.1, vector fields. We have already seen examples of vector fields when we discussed gradients. In general, a vector field in the xy plane is of the form of, we use capital F to denote the vector field, and the coordinate function, let's say this is f and g, they're both functions of two variables, okay? So f and g, they are functions from R2 to R. So capital F is a function from R2 to R2. It's a vector value function. Okay? And here are some computer generated plots of fields in each window. The origin is in the center. So when we draw the vector fields, notice that the length of the vector is not to scale, so that we don't want the arrow overlap each other, so we usually make the scale a little bit like smaller. So let's look at the first one, and we know the origin is in the middle. Let's say this is the origin, okay? So let's pick some points and plug in and check. If we pick the points 1, 1, okay, let's say this is a point 1, 1, then you can see the vector is also 1, 1. So that is why it's going to the right upper corner direction. Okay, what happens if we pick the points -1, -1? You can see the vector is also -1, -1. So it's going to the left bottom direction. Let's pick one more, probably 1, 0. So you can see this arrow is going on the right, okay, to the right. So and you can see when the point is near the origin, then the length, okay, so the length of the vector xy is so the length equals square root of x squared plus y squared. So you can see those arrows, they have smaller length, and then when x, y are far away, and the arrows is longer. Can you see from the picture? Okay, let's continue. The second one. Well, let's say origin is in the middle, and let's look at the points 1, 1. If we plug in here, we get -1, 1. -1, 1 is this direction. Can you imagine? And let's say if we're here, this is like -1, 0. Then y is 0, x is -1. So 0, -1 is going down. Okay, so you can see the direction field when we follow the curve, it looks like going counterclockwise. Okay, and also what is the length? Or the length is also square root of y squared plus x squared. So when the point is near the origin, the length of the arrow is small. When the point is far away from the origin, then the length of the vector is getting bigger. Okay, and this is the velocity of a particle on a rotating wheel. Okay, yeah. So let's continue. This guy at 0, 0 is 0. Let's see at 1, 1. Let's see here. If this is 1, 1, 1 minus 1 is 0. 1 plus 1 is 2. So it looks like at 1, 1, probably this is 1, 1. It's going up. Okay, and let's look at this point. Let's say if this point is -1, 0, then x is -1, y is 0, then we have -1, -1. So you can see -1, -1 is going this direction. So for each point, we just plug into our vector value function f, and then we can see what is the vector at that point. Okay, and you can see this when x is near the origin, the length of the arrow is small. When x is far away, the length is getting bigger. Okay, so let's continue. Okay, so next example, this is an electric field around a wire sticking out of the page. Okay, so have you seen this picture from your other course? Okay, so this is the electric field, and you can see well, when y is near the origin, our denominator is getting smaller, so the arrow is getting bigger. Okay, when it's far away from the origin, sorry, I think there's some typo. The 2 should be on the exponent, so it should be on the exponent. Okay, maybe when I when I copy these pictures, the word sort of shifted to 2. Okay, so yes, when x is far away, you can see the length is small. Okay, and this vector field is pointing outside. Okay, pointing out. Okay, next one. Oh, next one, you can see this vector field is pointing also, what do we say, counterclockwise. Can you compare those vector fields? This guy and this guy, they're pointing into the same direction, but just the magnitude change. Okay, and this guy, when the point is near the origin, the length of the vector is smaller, but this guy is the opposite. When the point is near the origin, the length of the vector is bigger. And also this guy and this guy, the direction are the same, but you can see the length is kind of opposite. When the point is near the origin, this length is small, but here the length is big. Okay, and y0 means we don't care what the x is, right? If for y equals 1, then the arrow, the length is 1, right? If y is negative, then it goes in the other direction. Can you imagine when when the point is far away from the origin, when y is bigger, then you can see the magnitude. The arrow of the vector is longer. Okay, the length of the arrow is longer. Oh, I forgot to say, the middle one is the magnetic field around a wire sticking out of the page. And then this is the shear flow of fluid. Okay, so vector fields are important because they can be used to model physical phenomena such as fluid flows, force fields, magnetic fields, etc. Okay. Next, gradient fields. We actually talked about gradient fields in chapter 12 already. Okay, some vector fields are gradient fields, while some are not gradient fields. So what is a gradient field again? It is of the form of the gradient of a function. Okay, so which means it's a partial of the function, partial x, and partial, this is phi, partial y. For some function phi is a scalar value function from R2 to R. Okay, so this function phi is called a potential function for the field, okay, the gradient of, so the field f equals the gradient of the phi. Okay. All right, so consider the following 3 fields. Which ones are the gradient fields? Which ones are not gradient fields? If there did exist a potential function phi such that f equals the gradient of phi, what would the level set of phi have to look like? All right, let's look at the first one. Imagine, let's suppose it is a gradient field. What is special about a gradient field? Well, the first coordinate is partial derivative with respect to x. Second derivative is second coordinate is the partial derivative with respect to y. And furthermore, we know for a function, usually the mixed partials equals. Okay, when the partial derivatives are continuous on the domain and it's open domain, right? And now let's see here. Let's check that. Okay, so what do we want to check? We want to look at the first function. We take the derivative with respect to y. Okay, let's call this is f. This is G. So this is in general a vector field, right? So we want to check F to the derivative with respect to Y. And then is that equals to G and take the derivative with respect to X. Okay, let's see. In this case, F is X. X take the derivative with respect to Y. This is 0. And then G is Y. Take the derivative with respect to X is 0. Yes. 0 equal to 0. So yes. This is this could be a gradient field, and can we find the function, the potential function? Okay, so think about what function we take the derivative, we get x. Well, that is like x squared, right? Because we take the derivative of x squared, we get 2x. But we just want to have x, so let's give it a 1/2. Okay, then the derivative of 1/2 x squared will be x. Okay, take the derivative with respect to x. And we want to take the derivative with respect to y equals y. So we also need 1/2 y squared. So actually this guy is the potential function. Then when you take the partial derivatives, you can get x and y. Alright, and what is the level curves? Well, you can see level curves, they are like x squared plus y squared equals a constant, and those are circles, right? Those are circles. And what do we know from chapter 12? We know that the gradient is perpendicular to the level curves. So the gradient is perpendicular to the level set. So far so good, and in this case you can see, yeah, it is. It's actually perpendicular to the level set. Okay. Next, let's continue. So let's call this is F, this is G. Then let's check. What is Fy minus 1? What's Gx? 1. Are they the same? No. So this guy can't be a gradient field. Okay. So far, so good. Yes, because the domains are all numbers, all points on the xy plane, and the mixed partial should be equal, but it is not. Okay, let's continue. This is F. This is G. So Fy is 1. Gx is 0. They're are they this? Oh. I want to say they're not the same, so they're different. Oh, we require them to be the same. So you can see they're different. So that's why this is not a gradient field. Okay. Now, let's find some gradient fields associated with potential functions. So here we're given potential functions. We want to find a gradient field. So let's see, partial t, partial x. Take the derivative with respect to x. 200 has no x, so it's gone. X squared, we have minus 2x. And what is ty? Well, ty is negative 2y, right? So what is the gradient? Well, the gradient is minus 2x minus 2y. So far, so good, everybody. Let's continue. So what is fx? Wow, this is chain rule. Do you still remember the derivative of arctangent? Well, that's 1 over 1 plus chain rule, right? The inner function square. So y over x squared times y over x prime. But this prime is taking the derivative with respect to x. So that's equals, okay, so that's y, and then times x to the minus 1. X to the minus 1 derivative is minus 1, x to the minus 2. Oh, so this is negative y over x squared. And here we can see, we can cut to the common denominator, we get x squared plus y squared over x squared. Now we can both multiplied by the x squared on numerator and denominator. That gives us minus y over x squared plus y squared. So far, so good, everybody. Alright, how about fy? Well, still chain rule. 1 plus y over x squared, but here y over x prime. This prime is respect to y. So that will give us derivative of y is 1. So 1 over x, 1 plus y squared over x squared. Let's multiply the top and bottom by x squared to get rid of the denominator in the denominator. So we have x squared plus y squared. Here we have x. So eventually our gradient of f equals minus y x squared plus y squared, and there we have x squared plus y squared. So far so good, everybody. Okay, let's continue. Let's look at this example. Consider the potential function phi and find the gradient field f. Show that the level curves phi equals to c is orthogonal to the gradient field. Okay, let's see. So potential function, okay, so what is phi with respect to x? That equals, okay, let's simplify it. This is 1/2 x squared minus 1/2 y squared, right? To take the derivative with respect to x, we have 1/2 times 2x. This is just x. And then, well, this is just minus y. So far, so good, everybody. So this guy is x minus y. So far, so good, everybody. Okay, and let's draw the picture. What is the level curves? Well, level curves 1/2 x squared minus 1/2 y squared equals to constant c. This is like x squared minus y squared equals 2c. Well, c is any constant, right? If c is 0, you just get the two lines, right? If c is positive, then we get some hyperbola. If c is negative, we also get some hyperbola. Can you imagine, everybody? And okay, now let's plot some points. At 0, 0, we see the gradient is 0. At how about at 1, 1? The gradient is 1 minus 1. 1 minus 1 is right here. See, it's perpendicular. How about, let's see, at the point 1, 0, then the gradient is 1, 0. Okay. Can you imagine? So you can see all the gradient is perpendicular, is orthogonal to the level set. And here, as to show it, actually we show it before. We show it in chapter 12, but it doesn't hurt to review it again. Okay, how would that work? Okay, so first, consider the level set. Phi of xy equals to c, right? And how do we get a tangent vector? Well, a tangent vector will be v. So let's think about okay, let's say we have a curve like this. Let's say the x component is 1. Then the y component is going to be the slope of the tangent line, which is dy dx. Okay? And so it will be 1, and this is dy dx. So far, so good, everybody? And last time when we talk about like the chain rule session, we also talk about the implicit differentiation rule. Okay, so we can differentiate this guy on both sides with respect to x. We get vx, and then dx dt is 1 plus vy dy dt. Dy dx. Okay, so that equals derivative of constants is 0. So dy dx is negative psi x over, phi x over 5y. Okay, so v is then 1 minus 5x 5y. Okay, and now when we dot the gradient, okay, so when we dot the gradient, the gradient of phi, dot v is then 5x 5y, 1 minus 5x over 5y. So that will give us 5x times 1 minus 5y times 5x over 5y. This cancel. Oh, 5x minus 5x equals 1. Oops. What did I say? Equals 0. Okay. So far so good, everybody. Yeah, sometimes it happens to me when I'm making these videos like over the summer. I make a lot of videos for different courses, so yeah, I've been making a lot of videos today. Sorry about that. Okay, now you can see we actually show that our gradient is orthogonal to our tangent vector. Okay. Okay, so the concept of vector fields and potential functions can be extended to three-dimensional space. So how do we find the gradient fields associated with the potential function? Well, let's take the partial derivatives with the three different variables. So phi x, okay, e to the negative z, stay there. Derivative of sine is cosine times chain rule. The derivative of x is just 1. Okay, so this is just this guy. And then phi y, e to the minus z, say there. Derivative of sine is cosine. But chain rule, y squared derivative is 2y. So far so good, everybody. Psi z, ooh, so this is gonna be a product. So product rule. When I do prime, I mean taking the derivative with respect to z in this part, okay? Plus e to the minus z second term derivative. Okay, e to the minus z derivative is minus e to the minus z. And then we have sine x plus y squared minus z. E to the minus z. Okay, derivative of sine is cosine. Oops. Okay, and then derivative of chain rule, derivative of the minus z is minus 1. So we get minus e to the minus z sine x plus y squared minus z minus e to the minus z cosine x plus y squared minus z. So far so good, everybody. Okay, finally, what is our gradient field? Well, phi x e to the minus z cosine x plus y squared minus z. Phi y e to the minus z cosine x plus y squared minus z times 2y. Phi z negative e to the minus z sine x plus y squared minus z. Oops. minus e to the minus z cosine x plus y squared minus z. Okay, so that is our gradient fields. Okay, so right now I want to show you how to use GeoGebra to graph vector fields and gradient fields. So when you go to our Calc 3 website, so look at the third projects, and I give you a PDF instruction. You can download GeoGebra Class 6, and I provide you a YouTube video. So I create this video and teach you how to graph the vector fields. I also give you a step-by-step screenshot. So after you look at the video, you don't need to like take the screenshot. You can come after you understand it. You can go to the notes, and then you can look at this step-by-step, and then you can input your function. So please make a different function. Don't make the same one. Also try to be creative. Okay. So here I draw two vector fields. The first vector fields, the coordinate function can be any arbitrary functions. So P is the first coordinate, Q is the second coordinate, R is the third coordinate. So you just input any arbitrary functions in terms of x, y, z. Okay, then we will get this guy. And let me make sure. Yes, see? You can see this this guy. You see the PQR. So you see this PQR. Okay, so that will give us that. And okay, and you can see this is the vector field. Okay, this is a vector field, and you can input different coordinates, and then it can generate different vector fields. Okay. By the way, A is the scale. So if you think the arrow, sometimes if you create a vector field, the arrows are too long, you can change the scale a little bit, make it longer or shorter. Okay. Yes. Okay. So this is the first vector field. You can just input the coordinate functions, and then it will generate a vector field. The second is the gradient field. So the gradient, let me see. Okay, so let me unclick this vector field and click the first one. So this is the gradient vector field. Okay, so you just input a different function f, then it will change the gradient vector fields. So we know, look at this guy. This is a ellipsoid, right? So that's why we can see the arrows is pointing out. Like sphere is a special type of it. Okay, so you can play with it. You can enter some different functions, and then this software can help you to calculate the partial derivatives, and it can plot the gradient field. So far, so good, everybody. Okay, so today we have introduced vector fields and gradient fields. And then we know that we call from chapter 12, we know gradient fields is orthogonal to the level surface or level set. Okay? And that's it for today. Have a nice day. Bye.